The last two tests that we have to talk about are ratio and root test. So the ratio test is something that you're going to see quite a bit of moving forward, mainly because we really like to use this whenever we work with factorials and exponentials. So the ratio test works well for factorials and exponentials. And we're going to see a lot of factorials when we start using series. So that's why we tend to use the ratio test. It also works all the time, which is nice. It's not one of the things that, oh, it has to fit a certain thing. Okay, now we may have an inconclusive situation, but it does work whenever we abide by the rules that are given. So here's the deal. Obviously, we have to be dealing with non-zero terms, and then we're going to have two situations. We're going to take the limit as n approaches infinity, which we've done before, but now we're going to compare the next term to the previous term. So we're going to do a of n plus 1 compared to a sub n. Now, as long as that is less than 1, we are going to be dealing with a series that converges. This is really similar to the geometric series test, and that we're going to compare this piece, and as long as that ratio is less than 1, we're going to converge. Now, when we did other comparisons, we were comparing a known series, right? We were looking at a p-series or a geometric series that we knew converged or diverged. This is not that case. We're just looking at the next term in this kind of sequence as we're adding these pieces together. So what is that next term doing? Is that next term less? And is that ratio going to be less than 1 as n goes to infinity? Now, the other thing that I want to make sure you grasp is that because we're putting absolute value signs around this, it does converge absolutely. That's something that we talked about whenever we dealt with alternating series, the difference between conditional convergence and absolute convergence. But these absolute value signs right here are part of the ratio test. So we're going to diverge in a situation when that ratio results in a value that is greater than 1. Okay, this includes infinity. So if you are going to evaluate this limit and you get infinity as the answer, that is considered greater than 1, so we are going to diverge. Now, we do have a scenario where if this is going to be equal to 1, if we do the limit as n approaches infinity and you get 1 as your answer, that's going to be considered inconclusive. It may conditionally converge. It may be divergent. We just don't know. All right, so this is going to be one of those deals where we may conditionally converge or diverge. So it's inconclusive. We would have to use another test. All right, let's see what this looks like and kind of this is very algebra heavy, but again, it works pretty consistently. So we like this test, and it's going to come into play whenever you use factorials and exponentials. So taking a look at 1a, obviously we would love to be able to use a geometric test. We would love to be able to use a p-series test. But when you see that factorial right there, it's kind of a dead giveaway that you're going to want to use the ratio test. So we're going to set up this ratio. We're going to immediately set up the limit as n approaches infinity. And what we're looking at is the ratio of the n plus 1 term. So we're going to do 2 to the n plus 1 over n plus 1 factorial. That's the n plus 1 term, divided by 2 to the n over n factorial. Now you notice I put absolute value signs around that. I told you guys this was going to be algebra heavy. We are going to have to change this. We're dividing by a fraction, right? This is a complex fraction. So we're going to change this into multiplying by the reciprocal. So 2 to the n plus 1. I like to just kind of go, okay, this times that, and this times that. Long ago, I was taught that that was kind of a sandwich situation. Okay, so the insides and the outsides, and you're always going to have that on a ratio test. So I'm dealing with that factorial, and then I've got 2 to the n over n plus 1 factorial. So now I've simplified that where it's no longer a complex fraction. I'm still required to reduce this, though, so that I can actually evaluate the limit. So I'm going to take a look at this. Obviously, if I've got 2 to the n plus 1 over 2 to the n, you could break that up if you want. 2 to the n times 2 over 2 to the n. But if you can just see it, you're supposed to subtract these exponents because they have the same base. You obviously end up with 2. So that is going to reduce for me. Now with factorials, we've also talked about that. We've talked about the factorial piece, where this would be n times n minus 1 times n minus 2, and we would go all the way down to where we'd finish that times 2 times 1. But the bottom starts at n plus 1. And we go to n, and then we go to n minus 1, right? And then we keep going. So I think it's relatively obvious that everything here is going to reduce except for that n plus 1 there. So we're left with a 2 that is in the in the numerator. 2 in the numerator. Right, and then we're left with that n plus 1 that's in the denominator. So I'm going to rewrite my limit one more time, and this is what I'm evaluating. I'm evaluating 2 over n plus 1. Well, now as n goes to infinity, I can tell pretty easily that that's going to go to 0. The question is not, does it go to 0 or does it go to infinity? The question is that result less than 1? Now, obviously, we're dealing with absolute values, so we're not going to get a negative result. Is that result less than 1? Absolutely. So we're going to make that comparison, and we're going to say, therefore, the series converges by ratio test.